Welcome to part 2 of chapter 18. We're going to jump in and start with nitration. So when we look at the nitration reaction, we are adding a nitro group, but we're using nitric acid and sulfuric acid. You might remember that from our nitration lab. This is going to replace a hydrogen with an NO2 group. Now, you must have the H2SO4. This won't work with just nitric acid. And it has to do with that first step, that creating a strong electrophile, right? Because it's not nitric acid that's the electrophile, it's a nitronium ion. So when we look into the mechanism, that first little step, right, again, the benzene doesn't come into play here. We're looking at nitric acid. There we go, it's nitric acid. We're going to take a proton from H2SO4 and we're actually going to add it to that OH. This is going to turn that OH into water, which is a great leaving group. So we have our nitrogen, our oxygen, and now water, which is going to ultimately wind up leaving. So in the second step here, you see a flow of electrons from the O- as we lose water, right? So we kicked off a water molecule. And now we have our really potent electrophile here, the nitronium ion. This is what is used in step 2, or in the second major part, right, where we are going to go ahead and add to the ring. Or substitute for the ring. We're going to have that electrophilic attack, that attack from the pi electrons to that positively charged nitrogen. Nitrogen's a group 2 element, so we can't have 5 bonds around it. So make sure you push off some electrons onto that outer oxygen. This is going to lead us into our sigma complex. Again, I'm not going to draw all of the resonance structures here. That's absolutely something that you should practice and feel comfortable with. I drew them in the very first reaction in part 1, and I will draw them again a little bit later when it gets a little bit more complex. But it is important that you know. Let's just put a little, let's make that more clearly a resonance arrow. There we go. And there are 2 other structures. Now, what is going to act as our base? Well, again, we're in strong acids, so we don't have anything that's a strong base, but we would have water around. Again, even the most concentrated of acids, unless you're just dealing with the gas, is going to have some water around. And that's going to help us regain aromaticity. And at this point, you can either abbreviate it and just write NO2, or you can show the Lewis structure and the charges. There's always a plus charge on nitrogen and a minus on the oxygen. So it is overall neutral. And you have that here on slide 19. So you've got the first step of creating the nitronium, the sigma complex, and then the regaining of aromaticity by removing that proton. Now, you do not need to know anything about the mechanism of this, but the way that we can add amino groups to a benzene ring is to add a nitro group and then to have reduced it. And the way you reduce it is with iron or zinc and HCl. All right, so I usually use zinc because it's similar to another reaction. It's just how I like to do it. And then you'll treat it with sodium hydroxide to neutralize. And that is going to, we'll draw it small here. That is going to reduce that nitro group, right? We're going to transform bonds to oxygen to bonds to hydrogen. This is really useful in synthesis problems. So we'll call it here reduction of the nitro group. Not responsible for the mechanism, just responsible for the reaction. So you can see how those are put together here. You take benzene, nitrate, and then reduce. Now, the next two reactions are linked, right? We are going to look at Friedel-crafts alkylations and Friedel-crafts acylations. They have some similarities, they have some differences. So the first one that we're going to look at is alkylation, where we are adding an R group, or substituting an H for an R group. We're taking our aromatic ring, and the reagents that are necessary are the alkyl chloride and then aluminum trichloride. Our Lewis acid catalyst has returned. And that is going to allow us to replace a hydrogen with an alkane. This does not work if you have an sp2 carbon that the chlorine is on. This must be an sp3 carbon with a chlorine. So you might want to make a note of that. So the first step in this mechanism of creating our electrophile, and I'm just going to use a very generic alkyl chloride here. It's going to look very similar to what we did in our halogenation. The halogen is going to form a bond to the metal, to the aluminum. It's going to donate its electrons to that Lewis acid, which will accept them. That's going to make this complex where you have a plus charge on the chlorine, a minus charge on the aluminum. When this CCl bond breaks, and we'll just go down this way, you're going to be left with a carbocation. The carbocation is going to be a much stronger electrophile than this partial positive carbon. And you will make AlCl4, which you will see again in the final step. That carbocation, we'll move up here. That's your electrophile, right? So that's what is going to be attacked by your pi electrons. You are going to make your sigma complex. You will have two other resonance structures. And then how are we going to remove that proton? Well, hopefully, this isn't terribly surprising. We have aluminum tetrachloride here, and we want to get our catalyst back so that AlCl bond breaks because we pick up that hydrogen and make a little bit of HCl. That regains our aromaticity, and we are left with the R group in place of the hydrogen. Now, when you're working on sapling problems, if they ever ask you for like the inorganic products, well, you also make a little bit of HCl. You regain your AlCl3, right? But if I ask you for the organic product, this is what I'm looking for. Now, there are some, and of course you have the mechanism more laid out on your PowerPoint. You can see those byproducts. There are some limitations here, right? So limitations and concerns. One of the big limitations, let's see, I want to go in order. Here we go. Is that you make a carbocation. what is able to occur when you have a carbocation? Well, if you think back to SN1 and E1, anytime you made a carbocation intermediate, rearrangements were possible. So if you're adding something small like this ethane, well, it's not going to rearrange. This C plus isn't going to be any more stable on this carbon. However, if you have a longer straight chain and you are creating a plus charge on a primary carbon, it's going to rearrange. Now, in this case, it's a concerted mechanism, but you could show it in two pieces if you wanted. This right here is going to be so much more stable than if the plus charge was on the primary position. So it's very hard to add longer straight pieces onto a benzene ring. They are often going to rearrange and your major product would be branched. Now that's why they started with the example of, let's see here, the 2-chlorobutane, because that's going to give you the more stable carbocation, so you're going to get primarily the product that you are expecting. So rearrangements can be a problem, right? Depending on what you want to make. If you want to put on a methyl or an ethyl or a branch chain, then it's no problem. But if you want to put on a straight chain, that can really be an issue. You also cannot use not used for sp2 carbon chlorine bonds. All right, so you absolutely cannot use a vinyl chloride. That will not work. You cannot use a phenyl chloride to do this reaction. That will not work. So if you're trying to add a ring, you have to find some other, or a ring like this, you have to find some other way. It must be sp3. Must, write this down, be an sp3 CCl bond. That carbon must be sp3 hybridized. It also can polyalkylate. Right? This means that once you add one R group, it's pretty easy to add multiple R groups. Now, it's not something I want you to worry about too much, but that is a practical concern. The reason that this happens is because R groups are electron donating, and if you are adding electron density into the ring, that only makes it more reactive. And finally, and this is important, especially for product predictions, Friedel-crafts reactions will not occur if a nitro group is already on the ring. Nitro groups have the opposite effect of R groups. They're electron withdrawing. They pull away so much electron density that this particular set of reactions will not work. Now, you could still add a bromine or chlorine or sulfonyl or another nitro group, but you cannot add an R group. So what would a problem like that look like? Well, I have no reason to draw it. It would look like this. If I gave you this, the correct answer would be no reaction or just the starting material. Now we're going to address some of these concerns with Friedel-crafts acylation, and let's take a look at that. The acylation adds a little bit different, but there are some similarities here, of course. You, instead of dealing with an alkyl halide, you're dealing with an acid halide. Now, it's important here that you note that this is an R group, not an OH, not an OR, not an amide. It's an R group. It's going to be carbon. So if you need to add something more interesting, you need to do additional steps. This will add a carbonyl and an R group. It also requires aluminum trichloride, and it will allow you to, and let's go off the top here, to replace a hydrogen with this acyl group. The mechanism starts off very similarly, right? We've got our acid halide. We've got our aluminum trichloride, and we are going to have that Lewis acid base reaction. You are going to make this complex, just like we've seen in the past, where we have a plus charge on the chlorine, a minus charge on the aluminum, and then this bond can break. Now, what we have created here, and then the AlCl4 is over there, is an acylium ion. This does not rearrange. So this handles your rearrangement issues. Now, you might be thinking, but it's not just a plain R group. Of course, we're going to handle that in a few minutes. So let's finish this reaction. Our acylium ion is our strong electrophile with that plus charge on it. And so then we go into making our sigma complex. The reason why it does not rearrange is it's resonance stabilized, right? That oxygen is keeping that plus charge here. There's no reason to rearrange. It's already more stable. All right, then the next part of the mechanism should look very familiar at this point. You have your acylium ion here, and you're going to have that attack. There's no reason. That carbon only has 3 bonds, so it can certainly take a 4th. You get your sigma complex, your resonance stabilized, positively charged ion. Again, I'm going to leave it up to you to practice that resonance. And what's going to act as our base here? Well, we have that AlCl4, and we want to get our catalyst back. So again, we're going to form a little bit of HCl. We're going to regain aromaticity. And voila, we have added our acyl group. Now, why this can be so helpful to avoid rearrangements is because you can reduce, right? So we're going to add another reaction you don't need to know the mechanism for, but this is the Clemmensen reduction. The Clemmensen reduction takes a carbonyl at the benzylic position, and it's a ketone or an aldehyde. This does not work for esters. This does not work for carboxylic acids. It's specifically ketones and maybe an aldehyde. And you are going to take a zinc mercury amalgam and HCl and heat. And what that's going to do is it's going to take that C double bond O down to a CH2. Just going to wipe that carbonyl right off. So this is one way that you could avoid rearrangements and make a longer straight chain. All right, so the positives, right, avoid rearrangements. There's a few other positives as well. It also avoids a poly substitution, because once you put on this carbonyl, that's actually electron withdrawing, so it's not likely to add again. And something to note, still does not work if an NO2 is already on the ring. So that was not changed or fixed, right? Friedel-crafts reactions will not occur if a nitro group is on the ring. Make sure that you note that. Now, in the next video, in part 3, we will discuss these substitution reactions on benzene rings that already have a group present.